To help preserve our planet, we have to change our collective relationship with plastic. But this does not mean abolishing plastic, because plastic itself is not the problem. It might not be so obvious, but the benefits of plastic extend into far-reaching areas of our lives. Plastic is highly resistant to aggressive environments and to most chemicals. It does not corrode and has a long lifespan. It is hard-wearing, flexible, and easy to look after. Our problem lies with small, single-use plastics, the kinds that are extremely hard to reuse or to recycle. Namely, shopping bags, straws, drink stirrers, coffee cups, takeaway food delivery boxes, and so many more. The COVID-19 pandemic has exacerbated this problem, and this happened without any significant improvement to the already inadequate plastic recycling infrastructures in place throughout the world. The majority of this plastic waste then escapes into the oceans, where it becomes almost impossible for our cleanup efforts to retrieve and recycle it all. So how can we keep the benefits while mitigating the shortcomings of plastic? Well, before we zoom in on the plastic issue, we have to zoom out, as far as the satellites orbiting Earth. This can give us an idea of the scale of our problem. To start this process, the European Space Agency has called out to teams of scientists from all over the world to come together to find solutions. But first, they must accurately and reliably identify the problem. To achieve this, we need institutions like Deltares, the largest water management and water research facility in Europe. Our hope is to be able to locate all of the plastic in the world. We want to find plastic before, during, and after it reaches our oceans.
The maturation of space also means that we can and we should use it for the actual societal problems that we have. And what does this mean? We need to address one of the biggest issues of this decade, if not the next decades. And looking at the start of this project, I think it's also beautifully demonstrating the value of what we can do. Because there was Paolo, an optical engineer, passionate like many of us about the environment, identifying that technical advances that we can have in sensors and on spacecraft, they could enable us to detect plastic litter.
The fascinating thing about satellite is indeed their potentiality to give a global perspective of something that we cannot have from ground. And the other thing that fascinates a lot for me about satellite is also the efforts that require to build a satellite. They are a magnificent tool that are sent into orbit. They orbit the Earth for years. So I think it's really a remarkable achievement for humans.
If you look at quite a few of our satellites, it's actually Earth observing satellites. So we measure the ocean currents, we measure the temperature, we measure or we try to predict the weather, the weather forecasting. Marine litter fits easily into that.
We put it out into our new open space innovation platform, and we tried to challenge the community saying, hey, we think this is possible, but we are not sure what are the best means. So we motivated the brightest minds that we could find, engineers, scientists, businesses, saying, hey, we would be ready to help you with the first steps, with the demonstration of the first steps. Come up with your ideas how you think we can do this from space.
That's also why I'm passionate about space. It's something that makes us look somewhere else from all the little difference that we normally pay attention to on ground.
It's impossible to build a satellite on your own. You always have to cooperate with different nationalities, with different levels of expertise. Not only the satellite, specifically the hardcore satellite technology, but also the people that are experts in terms of generating waves that are representative for the oceans, which is probably not typically what we would do here at ESA, but we're bringing people together so that the measurements that we perform with satellite instruments are as representative as you can get in the real ocean. It was really a no-brainer to go to Deltares.
Yeah, we have a long track history, of course, of modeling water flows and environmental flows for all kind of different things, and we can really contribute to this research with our knowledge on this flow behavior. We have less understanding how satellites work or radar, but it's actually really cool that we can work together with ESA. You see that people with different backgrounds are brought together, so we need to know something about plastics, we need to know something about the waves, we need to know something about the radar equipment, we need to know something about optical equipment, and you see that you have all different kind of specialists for these things, and we are finding each other in this research. And well, they want to have, of course, a big test facility where waves can be generated, all kind of ocean waves, and where we can throw in plastics, and that's yeah, we have this unique facility so that people can really see, oh, can I do it in this idealized situation? Can I get the plastics and track them back? If you cannot do it in this idealized situation, you can also not do it in the river, and then it won't work. So this is a first small step to see if you can track the plastics in this environment.
We try to gather evidence and scientific knowledge in a way that can actually inform policies. We don't try to direct policies in a certain way, but we try to make a realistic assessment of how things are, how things can be within a certain scenario if things change. Like, for example, Deltares is very good in assessing scenarios for climate change.
Satellite data is actually quite interesting because satellite data is coming, a satellite is flying over and over again. So you have at different time stamps, you have the same position of the satellite and the same data. So you can also see if things happen in time. And if you can then predict where the plastics are going to or where they are coming from, that might help policymakers to really to make policy to mitigate this, or to find the source. And if they take measures, after that you have to, of course, check if those measures are working properly, and then you need the measurements again, because then the satellite's still flying over the same area, and you can check, okay, what was it before and what is it after, and did we really improve? So those measurements which come in a sequence are very important for this whole process.
Remote sensing is sensing from a distance, so that can be on a satellite, but it can also be on an airplane or a boat. And I think it is very, very interesting because you're doing measurements and you're not disturbing anything. So although you always have to do field work, it gives you the nice overview that you need. If you use satellite data, you have repeat of measurements, and these are the positive sides of remote sensing, of course.
In terms of marine litter, I think space technology can really make a big difference on a global scale, because if you see how people are trying to solve it now, is they either go with a boat, but the boat, for a couple of days, they're sailing a certain track, they collect plastic, they count it, they weigh it, and then they say, okay, at this moment in time, for this particular period, there was so much plastic in the oceans. But that doesn't give you any idea, just 10 kilometers away from the track that they were sailing, what the situation is there.
We know basically nothing where plastic is going to end. We know more or less 1% of the fate of the destiny of plastic once it enters in the ocean.
And this is partially because plastic in the marine environment is subject to all the different environmental factors like waves, currents, winds. It can fragment, it can sink, it can be deposited on the beach. Plastic in the marine environment can have serious consequences to the marine life, as we probably come across seals entangled in fishing nets or whales that are full of plastic bags in their stomach. But let's say the impacts go beyond marine life and the ecosystems. It's not only about the pollutant in the sea. Even before it reaches the environment, mismanaged plastic has serious consequences for human health and well-being. And for example, the open burning of plastic waste in certain parts of the world, simply because there's not even collection of the waste. So we know that plastic pollution originates mostly from land-based sources, and because of the features of plastic being very light, very resistant, it can actually be mobilized and transported via runoff and rain through the rivers and into the sea. It's currently estimated that approximately 10 million tons of plastic enter our oceans every year. And unless there are dramatic changes, this amount can triple in 2040. So yeah, we just have to find ways, let's say, to tackle this thing at the source and not so much at the end of the pipe. And a good illustration of that is, for example, if you have a bathtub flooding with water, you can of course spend your energy taking the water out, but the first thing you try to do is to close the tap and then focus on taking the water out of the tub.
If you would do it only with field research, it would have to be very local, or you would have to, you would have to have many people being active. And I think this is actually happening with plastic, many volunteers. But the problem is so big that you need to get an overview.
So what we're hoping to do is to measure, to really provide scientific data about the problem. And that could be in terms of how much plastic is there in the ocean. Secondly, how is it distributed? Is there a sensitivity to the seasons? You know, is there a sensitivity to the wind? Are there certain tracers that we could use? And tracers, I mean, like, you know, maybe we're not detecting the plastic itself, but, you know, an effect of the plastic itself, for example, on the waves. Or is there always some sort of bacteria growing on the plastic that we can detect?
I guess the initial testing was we throw loads of plastic into the water, doesn't matter what kind it is, just put loads of plastic into the water and monitor it and see if we can detect that. Because if we can detect that, then that's great. That's like, at least we know the instruments are working for what we intend for them to do.
Then we started making the problem more complicated for each of the teams. So we started reducing the amount of plastic.
We want to precisely be able to detect and to know what's happened from each case, so we can lower the concentrations until we have some realistic ones.
Then we started saying, okay, now we start generating waves. So by doing that, we can try to determine the sensitivity of the instrument to detecting plastic.
What you have different type of waves. The waves we're testing here in the facility are the bigger waves, the ocean waves. But you also have, for example, capillary waves, and it's kind of, if you blow over the water surface, you get these small wrinklings, so that's the capillary waves.
With the waves, that became a lot more interesting because there's a lot of things changing like in the scene as you're monitoring. So you have the waves changing the signal, you have potentially plastic changing the signal, you have the way that plastic interacts with the waves changing the signal.
It was very difficult to see any change, okay? And that after 15 minutes of taking data, also you say, wow, from all the plastics that have been thrown to the channel, at most one has passed in front of my antenna. So I mean, it's what a pity, no?
One of the questions that is still unanswered is which technology is the best for detecting. So we had different groups in the campaign for Delta Ares, some experts in radar, some experts in radiometry, some experts in fancy technologies that, okay, maybe I shouldn't go into in detail, but they're all experts in their own field.
Plastic has a typical spectral signature, we say, so basically it reflects or it absorbs in a different way for different part of the electromagnetic spectrum. So that's what we are looking at. So the transformation of the sunlight reflected on the object and going back to the sensor. And we see there the change of the intensity per wavelength of the spectrum. We go from basically the visible, so very high resolution camera, to multispectral, hyperspectral. We go up to the thermal infrared camera, so there are several of them.
Yeah, in the shortwave infrared there are specific absorption peaks that are generated by plastic. The difficulty is that water absorbs in the shortwave infrared, so that if you have water on the plastics, you might not see the signal. So again, you need to have more information than just this one.
What we want to study here is try to comprehend how we can use the microwave frequencies, so in particular if you can use certain existing radar applications to overcome those issues and be able to detect plastic, whether indirectly or directly detect it. If it's possible to detect them, then it will be like very good, because the microwaves don't get impaired by weather, or are very good if there's cloudy weather, which is really good in open ocean, because the satellites can monitor those areas that are not accessible to optical sensors.
Microwave radiometry is the technique of measuring the noise, the thermal noise, in the radio part of the spectrum that is emitted by the bodies at a temperature different from 0 Kelvin. So it's like if you have a radio receiver that you tune into a band when there is nobody emitting, and then what you listen is basically noise. It's shh. So microwave radiometry is about measuring the volume of this noise. Okay? So in the case of the soil, if the soil is wet, the volume of this noise will be weaker, but if it is dry, it will be higher. We had 3 different transmitting antennas in different elevation angles, and we have receiving antennas at different heights and also different polarizations, because we wanted to see which was the behavior of the reflection in the presence of no plastics, flat water, no plastics with waves, and then with plastics, and see which were the changes that were induced in these 3 different scenarios.
I'm primarily focused on radar, but specifically synthetic aperture radar, so SAR. Synthetic aperture radar is basically a way to simulate having a giant antenna moving. So the satellite is moving and the antenna's moving, and it simulates the antenna being much longer than it actually is, which is the synthetic part of it. There's a transmit antenna and a receive antenna, and the transmit antenna sends out a signal which basically, depending on a multitude of factors of what the signal hits, the receive antenna picks up whatever's left of this signal and reads it into, for my setup, basically just goes through a VNA, so a vector network analyzer. I hope that's right. It reads how strong the signal was or where it came from, and then I can look at the raw data itself, or I can plot it into a graph. And so that means that if I knew that there was plastic in the water at 8 meters, and at 8 meters there is a change in the backscatter compared to when there's nothing in the water, then I can start to think, well, is it the plastic that's doing that, or was there another thing in the scene that's changing that, or try and figure out what it is.
The other theory is, does plastic damp waves? And by damp I mean that the height of the waves in a certain frequency might decrease. When floating plastic has its own inertia and size, most of it's bobbing up and down, and it hits some kind of resonance, and what that does is it enables it to travel faster than the water does. Because it's traveling faster than the water, it's taking energy out of the waves, and taking energy out the same way braking takes energy out is going to damp the waves. So that's what we're looking at. So this is being observed with ice flows, or sort of ice sheets, or slush even, and oil will do exactly the same things. With plastic, it's yet to be explored.
The results seem to be that they can see more with the capillary waves than with the normal waves. The normal waves and the dampening is, the waves are a bit too strong, most likely.
We have months of data processing and analysis to see what the signal is.
Now we have to understand how representative they are for the real ocean in terms of waves, in terms of amounts. Did we miss something in the first campaign? What do we need to do in the second campaign of measurement to really give, a scientifically sound answer? Can we detect plastic, yes or no?
The detection of plastic from space, if that comes out with this whole group project, would be an amazing outcome. Or even just the detection on, like, if it's at dams or in rivers where you see much higher concentrations. That's also a pretty exciting part.
Then, if we're able to detect it, and we're able to detect it in a certain way under certain conditions, that could imply that either we can use the satellites that we already have in space, maybe a bit of reprocessing the data or processing data in a slightly different way, or we would require a new satellite.
No matter which will be the results also of this test, it can be positive, but could be also negative, saying like, okay, we will need extreme density of plastic in order to actually have a significant and meaningful signal from space. Also, this would be actually a result, because we will know that at the moment we don't have to spend effort on these technologies. So we see that, okay, we need more spatial resolution, we need more spectral resolution, we need more sensitivity of our sensors. So we will need to work in technology to make a new sensor, new camera, new instrument to achieve this goal and fulfill the requirements that we are trying to define with all these tests.
Plastic detection is a very, very tough problem. Okay, so I'm pretty sure that not a single technique will do the job. It will be the combination of many. Some may perform better in some sea state conditions, or illumination conditions from the sun, or etc. So it's going to be probably the fusion of all this data that will provide the best result.
There's no single solution that can be just implemented equal in every way and then the problem is going to be solved. This is very closely related to our current economic paradigm, so it's a linear economy of take, make, waste. But it's also important to understand why is plastic being leaked into the environment. Is it because there's simply too much single-use plastic around? Is it because people do not have the right behavior and discard plastic incorrectly? Is it because the country does not have the right services and infrastructures to collect this plastic and dispose it in a correct way? So all of this is important information when we think about the concrete measures and solutions to prevent plastic.
Getting as many minds on it as possible is the best way of finding a solution, because eventually you'll have so many different ideas and so many people thinking over them that you can kind of break down what works best for everyone. And if each group comes in and tackles it a different way, you can work together to make sure each other's methods are as sound as possible. But also you might pick something up from another group and think, that's a really good idea that they're testing out. Why don't we try something similar on our end? Or why don't we say to them, have you tried looking at this?
What we already notice is that certain teams actually start measuring at the frequencies of the other teams so that they can cross-correlate results. Just to check, are we getting the same result? Are we getting different results? And if we are getting different results, why is that? So there was a very cooperative atmosphere. Sometimes, the equipment fails and the other teams jumped in to help the other teams to repair it or to get it running again. So forget the notion of competition. It was really absolutely working together to solve the problem. The data will be accessible to all the teams. Even more, it's going to be accessible to whoever wants to use it.
And people can look at the data and they can verify together with us whether what they see is right.
Satellite will not be the final tool that resolve and give all the monitoring of plastic, but will be one of the elements of what we call an integrated marine debris observing system, including satellites, drones, airplane, ground measurements, boat measurements, etc.
So hopefully after the second campaign of measurements, we will be able to set certain requirements that we need the instruments to have to detect plastic. If we're able to set requirements, then we can provide it to the project and say, if you would build a satellite that fulfills these requirements, we have very good hopes that we can detect plastics. And then it's up to the delegates and up to the top management of ESA to see if we can fly a satellite in the future specifically designed for detecting marine litter.
We have here a cotton butt stick, and the stem is made of plastic. In fact, this is being banned now in Europe, exactly because people, they tend to have the wrong behavior of disposing this into the toilets. Another way that people can contribute is to reduce the waste, to reduce the volume of waste. So for example, using a reusable bottle. And it's made of plastic, so it doesn't mean we need to ban plastic in terms of material. And another example, and this has more to do with the design, a toothbrush, which we in theory should change every 3 months, simply because we used the head. So all of this plastic goes to waste because of this part that we use. And this is a very smart solution. So this is simply a design solution to actually prevent waste in the first place. We have to be more mindful on the impact we have on nature, on how our way of living is actually affecting, and on all the benefits that come from having a more circular way of, and let's say a sustainable society in general. So yes, I remain hopeful. I think there's many challenges currently that we have to worry about, but yeah, I'm not losing hope.